All right, I'm going to record this just for the sake of it. Our story so far has been a story of concavity and points of inflection. And just to reiterate, we have a sine of f double prime theorem. Which is that if f double prime is positive, that means that f prime is increasing, which means that f is concave up. And f double prime is negative, which means that f prime is decreasing. It implies that f is concave down. Now, we also have points of inflection, and a point of inflection what is a point of inflection? X equals C is a point of inflection
if f double prime changes sign.
Changes signs, and he avoided the newbie mistake. In my other class, somebody, and we will not mention names, thought it was where f double prime is equal to 0. This is false. Not every 0 of f double prime is where the sign change occurs, and also not every point of inflection is where f double prime is equal to 0. It is also possible for f double prime to not exist. So a point of inflection will be where f double prime changes signs, because this is where f prime has a local max or min, which is where f changes concavity. Now I want to take just a minute to show you something about points of inflection and concavity. If I draw a function that is concave down and concave up, and it has a point of inflection right about here, can you all see that?
We all see.
These three, yes, exactly. These imply so. So, this is a point of inflection right here. Now, here's what I want you to observe. Where f is concave down, if I draw myself any tangent line to f right here, notice where that tangent line is. It is above the curve. The curve lies below its tangent. And the reason for that is that the tangent line has a constant rate of change, a fixed slope, constant slope. Whereas, when f is concave down, it has a decreasing slope, which means that if it touches at the tangent line right here, then it is going to lose, so to decrease in its derivative, where the tangent line keeps on going. Therefore, the curve will fall below its tangent line. So another way of saying that f is concave down is to say that f lies below its tangent. Meanwhile, over here, where f is concave up, I'll do this in a different color. F lies above its tangents. F lies above its tangents. And that means that if f changes concavity right at x equals c, right at this point of inflection, then the tangent line will actually have to go through the curve. I need to make it more tangent, like that. Everybody see that? Right at the point of inflection, the tangent line has to go through the curve because it has to be above the curve on this side and below the curve on that side. And the only way to do that is for the tangent line to go through. So right here, at the point of inflection, the tangent line goes through the curve. I will remind you of these things later, because we're going to do a whole lot of function sketching in January. Kind of like a one-a-day thing. Okay. Now at this time, I have about 10 minutes if you want to ask about any homework questions.
Number
Number 4, which says what?
says y equals to x plus cosine.
Yeah. And then we had to find out a whole bunch of things.
Yeah.
We had a discussion about this one in the other class as well. And what I'd like to do is I'd like to answer this question on a restricted domain 0 to 2 pi, and then come back and extend our answers to the entire real line. So the basic plan when you're dealing with trig functions is first work on the unit circle, 0 to 2 pi, and then come back and extend your answers using the fact that sine and cosine both have a period of 2 pi. Whereas tangent and cotangent have a period of pi. And secant and cosecant, because they are the reciprocals of sine and cosine, also have periods of 2 pi. So we're going to temporarily restrict ourselves to the domain of 0 to 2 pi, and then we'll come back and fix that at the end. And the questions that we're supposed to answer in this problem are find, what do we have to find?
Find intervals for which y is increasing.
Okay. Then,
And intervals for which y is concave down. And local extrema points of the inflection.
all right, so let's do this. To find intervals where y is increasing, I remember y prime greater than 0 implies that y is increasing, so I need y prime. And I take the derivative and set equal to 0. And this is the equation cosine x equals sine x, and I can either solve that with a direct appeal to the unit circle and observe that pi over 4 and 5 pi over 4 are the two places where sine x equals cosine x, or I could divide both sides by cosine x and solve that equation. And I get x equals pi over 4 and 5 pi over 4 as my two solutions on the interval 0 to 2 pi. I want to know where y is increasing. So I'm going to create for myself a well-labeled number line. And when I go plugging in angles, such as maybe x equals 0, I get a positive sign here, then a negative, and then positive again. So that I would say, for my limited domain, that y is increasing on the intervals 0 to pi over 4, together with union 5 pi over 4 to 2 pi. Because y prime is greater than 0.
Let's go back here.
Should be fine.
Yeah, thank you. Oh, for the first question, it's time just right, like here.
Does this make sense so far? Okay. So then, to find out where y is concave down, I need y double prime. So I continue on with y double prime, and y double prime is equal to negative sine x minus cosine x. Then again, I set that equal to 0 to find critical points of y prime. Which gives me the equation negative sine x equals cosine x. So back to the unit circle I go, and look for the 2 points where negative sine x equals cosine x, and that occurs at 3 pi over 4, and again at 7 pi over 4. Or again, I can divide both sides by cosine x and solve the equation tan x equals negative 1. Either way, I get 2 solutions. And looking at a number line for y double prime, then you can see that when x is equal to 0, I get negative, positive, and then negative again. So I would say that y is concave down. On 0 to 3 pi over 4. Union 7 pi over 4 to 2 pi. Good so far? The last 2 questions, I already have the information I need. Local extrema and points of inflection. For local extrema, I can look at the sign of y prime, and I can see that there is a local max at pi over 4 and a local min at 5 pi over 4 because of the first two tests. So I say y of pi over 4 is a local max because y prime changes sign, positive and negative. And y of 5 pi over 4 is a local min because y prime changes signs negative and positive. And finally, we have points of inflection at x equals, and I come back here to my y double prime number line, and I observe these 2 points right here, 3 pi over 4 and 7 pi over 4. Because y double prime changes signs. Yes, sir.
Isn't that a negative to positive or to
Correct, that's right. Points of inflection will be both types of sign changes. Yep. Are we good so far?
Yeah.
Now all we have to do is come back and fix the fact that we had a domain that was all real numbers. But that's actually very easy to do because of the periodic behavior of sine and cosine. If we extend the number line now so that it goes all the way out to infinity, all right through here, and if this is 0, and if that's 2 pi, 2 pi is actually honestly up here. Then when, because of the periodic nature of sine, when I go out to here, I'm taking a copy of this number line and just, boom, replicating it from 2 pi to 4 pi. And boom, replicating it from 4 pi to 6 pi. So that I'm going to have the same points that I had here, but each one of them will have 2 pi added to it. So the very next 0 that we have right here would be pi over 4 plus 2 pi, which would be 9 pi over 4. And the very next 0 after that would be 5 pi over 4 plus 2 pi, which would be equal to 13 pi. And because sine is periodic, my sines are going to continue to be just like that. And it happens in the reverse direction as well. So I come back over to this side here, and I can take this point and subtract 2 pi, giving me negative 3 pi over 4. And I can subtract 2 pi, giving me negative 7 pi over 4. And all my signs continue to be as they were on those intervals. Everybody see what I'm talking about? No? Question? Got it. All right. So how do I do that algebraically? Well, it's very simple. I go back to all of my answers right here, and I simply add an arbitrary multiple of 2 pi. So my increasing intervals over here are going to be 0 plus 2 in pi to pi over 4 plus 2 in pi. Union 5 pi over 4 plus 2 in pi, comma 2 pi plus 2 in pi. Just like that. And all of the rest of the answers are going to be just like that. My points of inflection are going to be at 3 pi over 4 plus 2 in pi and 7 pi over 4 plus 2 in pi, etc. Does that make sense to everybody?
What about concave down?
Same thing. Concave down on 0 plus 2 in pi, 3 pi over 4 plus 2 in pi, union 7 pi over 4 plus 2 in pi, 2 pi plus 2 in pi.
So they gave you a one day.
So it's all real numbers.
So we are just assume that it's like 0 to 5 and then
Temporarily,
later.
yes. We temporarily restricted it to 0 to 2 pi because that's one full unit circle, and then we came back and extended it to any number of rotations around the unit circle.
Every 3.
Every 3 problem.
For polynomial loop action, can I just write 3 pi over 4 plus n pi? Because the sign is fundamental.
Yeah. If I understood you correctly, yes. So, Jason, generally you said every trig problem. The real key here is to know the period of your problem, right? So if you're working with tangents, it would actually be plus n pi. Right? Good. Does that help? I want to talk about one problem that came up in a couple of assignments ago, and that was to graph y equals the absolute value of x squared minus 4. You guys remember this one?
Yeah.
Yep. And in the graphing, we needed to identify local extrema. And then, and so we did the usual things, and all of you did find the derivative here. The derivative of the absolute value of slack is slack over the absolute value of slack times the derivative of the inside. So we get this. And now we need to consider the critical points, but remember that there are critical points of two types, where y prime equals 0 and where y prime does not exist. So we end up with this sort of interesting thing. If I set y prime equal to 0 first, of course a fraction can be 0 only if its numerator is 0. And so when I factor that completely, I observe that I have 3 solutions for my numerator equaling 0, and those are x equals 0, x equals 2, and x equals -2. But when I try to find the places where y prime does not exist, a fraction will not exist if its denominator is 0. I set the denominator equal to 0, and I get 2 solutions, 2 and -2, again through factor. So my question is, which is it? Does y prime of 2 equal 0, or does y prime of 2 not exist? Which one of these matters most? Yes, because it is impossible to divide by 0, therefore it is the case that these 2 solutions are spurious solutions. Yes, they make the numerator equal to 0, but 0 over 0 is not a number. Does that make sense to everybody? So this matters because when I graph this, I'm going to graph y prime equals 0 very different than I will graph y prime does not exist. Y prime equals 0 means I have a horizontal tangent. Whereas y prime does not exist is going to give me one of my points of non-differentiability, such as corner cusp, vertical tangent. And when I check the form for y prime at 2, my form for y prime at 2 and also negative 2 is 0 over 0, which strongly suggests that what I'm looking at is a corner. That I probably have some kind of common factor in there that's going to cause my derivative to be one value from the left, one value from the right. That kind of thing. Does that make sense? So, when I construct my number line is going to bless you. My number line is going to look like this. I've got my 3 critical points here, but I will not mark them in the same way. The points at negative 2 and 2 I will mark with an X to indicate that my derivative does not exist, whereas the point at 0 I will mark with a 0. And when I come back and plug in to the intervals there, what I find is that my derivative signs look like this: minus, plus, minus, and plus. I'll let you work that out for yourself. And when I graph y, now comes the important point. Y of minus 2 is a local min because of sign change. By the way, are you guys getting a little tired of writing because the sign of y prime changes from minus to plus? Good. Good, because it needs to become a habit. You just do it, right? So I'm okay if you're tired of writing. Me too. And y of 0 is a local max. Now when I'm graphing, it makes a lot of sense. It makes a lot of sense for me to find these values here, so that I know how far down to go and how far up to go. And so I take y of minus 2, and I plug x equals negative 2 into y to find y of minus 2, and I get 0. And I also get 0 for y of 2, and I get 4 for y of 0. And so this gives me 3 points. So, got my 3 points, and now I'm ready to sketch my graph. I'm going to have f be decreasing, then increasing, then decreasing, then increasing. But when I come down to negative 2, I'm going to draw it so that it is very clear that I have a corner there. Whereas at x equals 0, I want to draw it so that I have a horizontal tangent. And at x equals 2 again, we have another corner. Yes?
How do you know this?
So to verify that it is a corner completely, what I need to do is to find, remember that the definition of corner is that the derivative from the left is a different value from the derivative from the right. And I need to actually go and compute those derivatives. We will practice doing that tomorrow, but for today, I did a quick and dirty kind of thing. I looked at the form. And because my form was 0 over 0 and not k over 0, that told me my derivative was not infinite. And because the derivative is not infinite, well, there you go.
So the cost, the form cost is also
K over 0. Because it's infinite. Negative infinity from one direction, positive infinity from the other. But if I actually want to verify it, and I'm asking how do I know, then I would compute these guys, the limit of the difference quotient. That. And when I do, this limit right here for x's that are a little bit smaller than 2 is going to give me negative 1. Whereas this derivative right here
It's a positive.
gives me positive. And because those limits are different values, yeah, this is x minus 2. Sorry. Good. You guys are doing well. Main story for today is the second D test, the second derivative test. And our setup is this. Suppose that f prime of c is equal to 0. Now, what does that tell me if I know that f prime of c is equal to 0? Lots of different things here. First thing I know is that the graph of f definitely has a horizontal tangent.
So along the line.
Could be, that's right. Right. The second thing that it tells me is that it's that I have a critical point there, and it may be the case that I have a local max or local min. May be the case that I have a local max or min. So one way that I can test that is to use the first D test that you know and love. I can look for sign change at x equals c. And if f prime changes signs from plus to minus at x equals c, then f of c is a local max, etc. But there are times in our lives when evaluating the sign change is hard or impossible because we don't have enough information or because the function is hard to work. And so a second way that we could look for max or min is to look at the concavity of the curve. What do I mean? Let's take a look. Suppose that f is concave down at x equals c on an interval between x equals c. And suppose I have a horizontal tangent. That critical point has to be a local max, because the curve lies below its tangent line. Yes. So a horizontal point of horizontal tangency at a point where the curve is concave down must be a point where we have a local max. So we can say it like this. If f prime of c is equal to 0, and, second condition, f double prime of c is less than 0, then I know that f of c is a local max. And the picture here is this picture right here. Furthermore, if f prime of c is equal to 0, and f double prime of c is positive, now what picture do I draw? I draw a picture where my curve is concave up, and it has a horizontal tangent. I've got a local min. Yes, sir.
So, the question for the tangent line is at x equals
Exactly so. This is going to be the point C coming out of C.
We would have a graph like two local max, but it's not even the same level.
Actually, either the first D test or the second D test will pick both of those up. So we'll handle that in just a second. But first I have to ask, did I leave out any possibilities? What else, what other possibilities could I have besides f double prime less than 0 or f double prime greater than 0? Equals 0 or does not exist. In both of those cases, sadly, the test fails. It does not tell me anything. Then you have to do the first t-test, that's right. And you want to use the first t-test on it. Now, you may ask, well, if we already have the first t-test, why would we want the second t-test? I want to show you two instances where you would want to use the second t-test problem. Yeah?
If we can use secondary data, we recommend use secondary.
That's a great question. The answer is use whichever test is the easiest for you. Now, I say that, students will say, well, I know the first t-test really well, so I'm just going to do that all the time. I don't mean that. It turned the second t-test into the ugly stepchild. You don't want to do that. Instead, learn both tests, be good with them, but then when you look at a problem, say, what's the easiest way to get there? Let me show you an example. On the local extreme, f(x) equals x cubed minus 3x. Okay. Now we know that local extrema only occur at critical points, so our first job is to find the first derivative and set it equal to 0. That's true whether I intend to use first or second t-test. I need those critical points as my candidates. Now, if I wanted to do a first t-test, at this point I would do an f prime number line. I would identify intervals increasing, decreasing. I would look for sign changes. However, the second t-test is really easy to use here. Here I have 2 points of horizontal tangents, x equals 1 and x equals negative 1. And I can find whether those are local maxes or mins by just looking at the concavity at those points. So, I'm going to find f double prime, which is equal to 6x. And I'm going to evaluate that at my first candidate, which is x equals 1, and I get 6. And the evaluation is that that is greater than 0, which tells me, and if you're confused, draw a picture, concave up, horizontal tangent, local min. We've already provided the justifying reasons. F prime is equal to 0, and F double prime is greater than 0. And those are the two conditions for my second t-test. Yes?
Yeah.
That's it. What I've got right there, that's the format.
So we don't have to use
You've already provided the justification. You've already provided the justification when you observe that 6 is bigger than 0. And when you observe that f prime is equal to 0. Remember that the second t-test has two conditions. F prime equals 0 and f double prime is positive or negative. We're going to test the same thing at x equals negative 1. F double prime of negative 1 is equal to negative 6, which is less than 0. And that implies, therefore, that f of negative 1 is a local max. And that's it. So here you can see that in this circumstance, the second t-test is really easy to use. Yes?
So, the purpose is
The purpose is the same, to find extreme.
to find local maximum. Two different ways.
Two different ways to do it, right? And it all depends upon what information you have. if I have a graph of f prime, I'm gonna use the first t-test. Yep. Let's do another example. So I find my first derivative, first times the derivative of the second, plus the second times the derivative of the first. We've seen this function a couple of times now, right? Set that derivative equal to 0. How do I solve? Factoring, yes. And what solutions do I have?
X is
Exactly. Right, exactly. So I get a single critical point at x equals -1, a place where f prime is equal to 0. So now I have some options. I could try a number line, right? Or I could try the second d-test. The only thing I need for my second d-test is a second derivative. So I go back to this guy right here, and take the derivative, and write that out so you can see my steps here. I get first times the derivative of the second, plus the second times the derivative of the first, plus the derivative of f prime. And I can now evaluate my point of horizontal tangency for its concavity by plugging in x equals -1. And when I do, I get negative e to the -1 plus 2 e to the -1, which is e to the -1, which is a positive number. Remember that e to the -1 is the same as 1 over e. And so I conclude, therefore, that f of -1 is a local min. And if you were confused about that, draw yourself a graph, concave up, horizontal tangent. So the second test is pretty useful. Now, let me show you some circumstances where the second test might not be a great idea. Okay, so we are of course going to need the first derivative. So we take the derivative of outside times the derivative of the inside. Clean it up a little bit. And there's my f prime. Now I want to consider critical points. First of all, I consider where f prime is equal to 0. Which happens where x is equal to 0. Then I consider where f prime does not exist, which is going to happen where 1 minus x squared is equal to 0, so that x is equal to 1 or x equals -1. I observe that my original function here has a restricted domain. What's the domain of my function?
square value to 1? Or no?
Number is less than one, like -3. Greater than -1 and less than 1. Domain is going to be determined -1. And you can see why. So my critical points here actually happen at endpoints of the domain. While I'm thinking about it, let me check the form real fast. And the form for both of them is either 1 or -1 over 0. Which means that I've got some kind of vertical tangent. Right at the endpoints of the domain. Everybody see what I'm talking about? The form for f prime at 1 and -1. Plug in f prime. Yeah, got it. Okay. So now I consider I've got 1 point of horizontal tangency, and I've got 2 points where f prime does not exist that are at the endpoints of my domain. Because they are at the endpoints of my domain, I am not going to consider them for local extrema, because local extrema occur on open intervals, and cannot therefore occur at the endpoints of the domain. So we're not going to consider those. We're going to consider only x equals 0. So what are my options? I could do first d-test, or I could do second d-test. If I do the second d-test, I have to find f double prime of x. And that seems costly to me. So thinking over here, here's my thought bubble. First D or second D. And I look ahead and I see that f double prime of x is hard to compute. And because it is hard to compute, that pushes me away from the second D test and into the arms of the first D test. So I will construct for myself a well-labeled number line, f prime, with a 0 here. My domain is restricted, -1 to 1. And if I plug in some value for x, maybe -0.5, then I get a positive value here. If I plug in +0.5, there it is. And I conclude, therefore, that f of 0 is a local max because f prime changes sign from positive to negative. Before you go, let's take a quick look at what the graph has to look like. At -1 and 1, according to my analysis, my derivative is infinite. And so I have a vertical tangent right there. Then I have a horizontal tangent, and then a vertical tangent again at 0. So my graph looks like this. In fact, it's poorly drawn, but it's supposed to be a semicircle. Yes?
The domain includes -1 and 1.
It does include that. So notice I did not say vertical asymptote, but vertical tangent. And the difference is that a vertical asymptote, the function goes to infinity. For a vertical tangent, the function exists, but its slope goes to infinity.
You don't have to consider a function.
We don't have to consider them for local maxes and mins to answer the question.
But it includes the
But they are included in the domain of functions, yes. Go back to the definition of our function right here. F of 1 is the square root of 0, which is 0. Perfectly valid number. So f of 1 exists. It's a point on the graph. But if I draw a tangent line to it, that tangent line will be straight up and down because the derivative is infinite.